Let's do an example about Charles' law. So we have a sample of gas with a volume of 2.80 liters at an unknown temperature. Take that sample of gas, submerge it in ice water at 0 degrees Celsius. The volume decreases to 2.57 liters. What was its initial temperature in kelvins and in Celsius? So you read through the whole problem, then you make a table, pull the numbers out, and organize them. So we have a condition 1 and a condition 2. And it doesn't matter which one you call which. You just have to get them together correctly. So we have 2.80 liters at an unknown temperature. So 2.80 liters, that is a volume. The temperature we don't know. And then it says that we submerge it in ice water at 0 degrees. So the second set of conditions where it's submerged in the ice water, the temperature is 0. And the volume shrinks a little to 2.57 liters. So we're looking for T1. Can we use 0 degrees Celsius? No, we have to convert this to Kelvin. So to convert to Kelvin, we add 273. And so this is going to be 273. Kelvin is the temperature. Now we need our equation. We have volume and temperature, so we're going to use Charles' law, V1 over T1 equals V2 over T2. It's equations like this that students really mess up when they rearrange them because there's a fraction in there, and just to make it worse, we're solving for something in the denominator. And so then people end up doing very odd things. So to avoid doing odd things that get you an incorrect answer, get rid of the fraction by cross multiplying. So we're going to take, let's do a different color here. We're going to take the top of one side times the bottom of the other side, and that is going to equal the bottom of the first side times the top of the other side. That's cross multiplying. When we do that, we end up with V1 times T2 is equal to T1 times V2. We're solving for T1 because that's the blank in our table. So I want T1 by itself, so I'm going to divide by V2 because V2 divided by V2 is 1, and that just gives me T1 on that side. But to keep this equal, I have to do the same thing to both sides. So I'm going to divide by V2 on the other side. Good idea to rewrite the equation. T1 equals V1 T2 over V2. Very easy to mess up the 1s and 2s. Try to avoid doing that. So volume 1 is 2.80 liters. Temperature 2 is 273 Kelvin. Volume 2 goes in the bottom, and that's 2.57 liters. Look at what happens to the units. We have liters divided by liters. Those units cancel out. So I'm left with Kelvin. So I get out my calculator, and I've got 2.8 times 273 divided by 2.57. And that's going to equal 297.4. That's more than enough significant figures Kelvin. I should have 3 sig figs in this answer. So that's the initial temperature, 297 Kelvin. It wants the answer in Kelvin and in Celsius. To convert to Celsius, we're going to subtract 273 and 24.4 degrees Celsius. So my answer then, there's two answers, 297 Kelvin or 24 degrees Celsius. Any questions? What answer would I get if I forgot to convert to Kelvin? If I put in 0 here for T2, then T1 would also be 0. Does that work? No, it doesn't. It doesn't. Because why would the volume change if the temperature didn't change? This equation does not work with Celsius. And that's because the conversion between Celsius and Kelvin involves adding. It's not just multiplying. This will work with liters, milliliters, gallons, microliters. You can have any volume unit because those are all related by multiplication. But because temperature conversions involve adding or subtracting, you have to use Kelvin. Okay, any questions? Another problem. A gas in a cylinder with a movable piston has an initial volume of 88.2 milliliters and is heated from 36 degrees Celsius to 155 degrees Celsius. What is the final volume of the gas in milliliters? Read through the problem, make a table. I have condition 1 and condition 2. The first number is 88.2 milliliters. That's volume, so I'll call that column V for volume. Sometimes it's a little unclear to a student, which temperature does that volume go with? You have an initial volume, and you're heating it from 36 to 155. So the initial volume goes with the 36, the initial temperature. And if you need to draw a picture, draw a picture. Sometimes that really helps to draw a picture. So the temperature is our other unit or our other variable here. 36 is where it started, and 155 is where the temperature ended. Anytime you see degrees Celsius, always just convert it to Kelvin right away, because otherwise you'll forget to do it. And the thing is, almost always, the problem will give you temperatures in Celsius, and you have to convert to Kelvin. So 36 plus 273. This is a day when I don't trust my head, so I'm going to use my calculator for that. That's fine. 309 Kelvin. And 155 plus 273, 428. So I have one blank in my table, and I'm going to call that V2. Now again, I need an equation that gives me T's and V's only. I'm going to give you the gas law equations on the exam. So all you have to do is find the correct equation and rearrange it. You don't have to memorize these. So you can look it up. V1 over T1 equals V2 over T2. Again, this equation has fractions in it. Get rid of the fractions and then rearrange. So V2 times T2 is equal to T1. See, I screwed that up, didn't I? That's not V1. V1. So the top of this, V1 times T2 is equal to T1 times V2. Very easy to mess that up. So this time I'm solving for V2. V2's over here. So I'm going to divide by what's with it, the T1. T1 over T1 cancels out. And I have to do the same thing on the other side. So the new volume equals the original volume times the second temperature divided by the first temperature. Again, this is not the only way to solve these problems, but it's the one that seems to work best for 3A students. So there's our initial volume and our final temperature, 428 Kelvin, divided by T1, 309 Kelvin. Looking at the units, the kelvins are going to cancel out, so that's a good sign. If your units don't work out, maybe you rearrange the equation incorrectly. 88.2 times 428 divided by 309. My calculator is showing me 122.16699, blah, blah, blah. Looking at these numbers, none of them are exact. They all have 3 significant figures. My answer should have 3 significant figures. The unit is milliliters because that's the only unit that didn't get crossed out. So the volume is 122 milliliters. Any questions? I forgot to do this on the previous example. It's always a good idea to ask yourself, is it reasonable? So here we're taking a gas and we're heating it up. Do we expect it to expand for the volume to get larger or to get smaller when we heat up the gas? We expect it to get larger. And 122 is larger than the starting volume, so that's a good sign. If it went the other way, that means you've got something backwards.